Good afternoon. It's time to start the seminar of Professor TSUZAKI. At first, I would like to introduce Professor TSUZAKI. He is a managing director of Research Center for Strategic Materials of National Institute for Materials Science. He is also professor of Materials Science and Engineering of University of Tsukuba. He received a Doctor of Engineering in Material Science and Technology of Kyoto University in 1983. He was postdoctoral fellow at MIT in 1983 through 1985, and research associate and associate professor at Kyoto University. Then he joined the National Institute for Materials Science in 1997. He is one of worldwide researchers in materials science. For example, his research findings appeared on Science. The title was Inverse Temperature Dependence of Toughness in Ultra Fine Grain Steel, Fine Structured Steel. This is epoch making for us because science and nature hardly accept a research result of steels. And today, lecture of Professor TSUZAKI is stronger, tougher steel, potential of nanostructure steels. Professor TSUZAKI, would you start?
Thank you, Professor MATSUOKA, for your kind attention to me. Good afternoon, ladies and gentlemen. My name is Kaneaki TSUZAKI from NIMS Tsukuba. NIMS is a National Research Institute for Material Science in Japan. And I'm very happy to be here to make a presentation today for you. And firstly, I have to apologize you because of the date of seminar today. It is just before national holiday, Obon holiday. And or it's already in it for some people. So I apologize for your convenience of the date. But when I had decided the date of this seminar, I only considered it is okay because the 12th Friday, not 13th Friday. Okay, it's okay. Okay, everything is done for me. But I'm sorry, but I'm very happy because I have many students and professors and researchers in this room. When I start my talk, let me say you something. I found things in Fukuoka. 3 things: changed, unchanged. Firstly, JR Hakata Station and the station bill have been changed completely. Okay. Well, I came Fukuoka before 1 year ago. So then, well, it's been completely changed. Looks very fine. Secondly, it isn't changed. That is the taste of a Japanese noodle, udon, in Daifuku udon. In, there was a shop in Ekisaido Yokocho. Right, the soup of udon noodle was completely same when I was a high school student in Fukuoka. And thirdly, actually, it is changing. What is changing is Ito campus, Kyushu University, especially a research facility related to hydrogen research. So the laboratory tour of 1.5 hours with Professor MATSUOKA has strongly impressed me. What a fantastic research circumstance here. Oh, I have a strong jealousy to it. And how much research budget you obtained every year. I wouldn't like to know that because of I don't want to get another jealousy to you. Okay, anyhow, okay, today's title is about steels, okay? I'm afraid most of the people has a wrong impression about the steel. That is the old material, okay? If there are some people here with such an impression, the aim of my talk today is change it, okay? And why? Steel has a very high potential yet come with the nano-structured material, microstructure, I should say. So, outline is you have outlines of today's slides. Okay, so I follow these slides. In the introduction, I will consider which property limits steel development. And then I'd like to introduce the two topics in the steel property. Actually, two jumps in steel property. One is a jump in the impact toughness of bar steel with the grain definement. You may know a grain definement is now very popular in all kind of materials because grain definement gives you a better property. But what kind of a better property you can get in steel? And next is about the strength of a steel bolt. We had a jump. And it is associated with the nanoparticles. So today, I'd like to talk, so grain definement and nanoparticle. And the property is a toughness and strength. So then my title is stronger and tougher steel. Okay, and I may say something in a concluding remark. So, low carbon society and sustainable society. If you consider the circumstance that you want to obtain, you need stronger steels and lighter steels. So the demand for low carbon society, is it okay? All right. So, but please remember this. Few structural materials are limited by their strength. Rather, they are limited by their resistance to fracture. So then what or which property are steels limited by? The answer is toughness. Okay, so toughness is very important, not only for human beings, but also steels. Okay, because we need safety and reliability for construction materials. So the toughness is the key word. And this is a very popular figure for steel researcher. I took this figure from the textbook of Professor George Krauss. And this figure tells you strengthening isn't difficult in steel because you have a multensitic transformation in steels. And multensite is a very strong phase. This is the hardness here. And this is the carbon concentration. This is the data of iron-carbon binary multensite. Its strength and hardness increases sharply like this. And if you get a carbon content of 0.4 mass percent, then you can get the strength level of 2 gigapascal. So you can, if you want to get a stronger steel, please do quenching after heating at around 1000 degrees centigrade. Then you can get the 2 gigapascal if your carbon concentration is about 0.4 mass percent. However, good things and bad things. Drawbacks of high-strength steels, there are several. And the toughness, hydrogen embrittlement, and ductility. This figure shows the one example how the toughness decreases with the increasing yield strength for titanium alloy, low alloy steel, and high alloy steel, blue, pink, and brown bands. This is the absorbed energy, sharply absorbed energy, impact energy at the ambient temperature. Like this, even in the titanium alloy, that toughness, impact toughness, sharply decreases like this. So I'd like to say I was in charge of ultra steel project. It started 1997, where there are very high level of research target in property. So one of the target was the toughening of low alloy steel with the yield strength of 1800 megapascal. Let us look at the target on this figure. 1800 megapascal is here. And toughening here, Professor Matsuoka, what is the limit? Okay, the necessary impact energy usually for engineering material. So some people said 70 joule, okay, 70 joule at minus 20 degrees centigrade. Can I ask somebody? Well, anyhow, I discussed with the several researchers at the time, and their demand for impact energy was 100 joule for safety. So then target becomes like this. Okay? Then you can find no material exists to meet this target. Okay? So steel, material steel has a long history, but never produced this mechanical property. Then this is the challenging. Okay? And that time, people worried about the addition of too much alloying content, such as the cobalt, nickel. Those are very, very expensive. Okay? So then low alloy steel would be another key factor. Then today, I tell you the jump of a property from this to this. The chemical composition isn't changed. This chemical composition shows this value with the conventional heat treatment. However, this property increased up to here with the special processing that produces the new type of microstructure. So, so then, since our target is the completely frontier. So then we need a new idea to obtain it. But since the research work of grain refinement has been continuing at that time, so then firstly we consider the utilization of a grain refinement. Then the question is grain refinement effective for our purpose? Answer is yes, it is. So you know there are many things, okay? I think most of people know that grain refinement makes a material tougher. However, I should say it isn't enough. Okay? Partly yes, but partly not. And this is the very famous data reported by Professor Takaki, who is sitting there. If I make a mistake on it, please check it. Like this. So what this figure tells you is this is a ductile-brittle transition temperature and versus the grain size. Grain size is finer in right. Professor Takagi did some mechanical controlling processing on low-alloy steel. Then ductile-brittle transition temperature decreases like this. So above this line, your steel behaves ductile. But below this, materials shows brittle in the fracture mode. So then you can get a safer material when the grain refinement has been done. But when you look at your absorbed energy, okay, well, I should say, this is telling you change or I should say, a transition in a fracture mode. Okay? This doesn't say anything about the absorbed energy with the ductile mode. This is the energy. Energy is higher than 200 joule when the grain size is around 5 micrometer. But this value decreases like this with the grain refinement, and then lower than 100 joule. So what I want to say is, upper shelf energy is decreased by grain refinement. See? So then the ductile fracture isn't a necessary condition. I need energy, absorbed energy higher than 100 joule. So then I should say a high absorbed energy is a sufficient condition for structural steels. So then we discussed the again and again, and there was the one good hint. If you know about the name of a cipher, scientific ferrite, Fe, and I don't know exact name, okay, but this is a nickname, okay, nickname. And this cipher shows the significant ductility even at the very, very high strength level of 5 gigapascal. And this steel has been produced by a process of drawing. And please look at this. This is a true drawing strain. And this is a tensile strength. So 5 gigapascal of strength is achieved by a 99.99 drawing reduction. Very high drawing reduction ratio. And this is the picture after tensile test. And this wire can bend, and this is some tie here. So when you look at the microstructure, so fine grain, very fine grain, 50 nanometer of a grain size has been produced this severe plastic deformation. And grains are elongated, no longer equiaxed and elongated, and texture, crystallographic orientation texture shows a typical drawing texture. 110 BCC parallel RD is a rolling direction. So I thought, or actually my young colleague thought this elongated grain structure along with the fine grain size would be a hint to obtain a high ductility. But as you can see here, severe plastic deformation is necessary. And product size is very tiny, less than 100 micrometer in diameter. So it is okay for wire or fishing. But we cannot produce any engineering material with this processing condition. So then, how to realize an ultra-fine elongated grain structure in a large scale product? It's another challenge, I think. Okay? Once you can get the possible or attractive microstructure, then you have to consider how to produce it. You have to consider the processing. Okay? So the processing, what you have to consider the size of a product, okay, and the cost of a product. Those are the conditions. So in this case, but we wouldn't like, I don't like to take the severe plastic deformation. So then another hint is here. This shows how the microstructure changes with the total strain when you changed the initial microstructure before deformation. One is the conventional ferrite with the coarse grain size. The other is a martensite with the very high, with the small grain size, even as quenched condition. As you can see, the tendency of a grain refinement, its kinetics is much faster in martensite than ferrite. So this means initial microstructure of a grain size is finer, then kinetics is faster. So the only strain of a 2 is necessary to produce this fine grain elongated structure. So then we decided this chemical composition of a steel and processing. And the chemical composition is the 0.4 carbon, medium carbon content, 2 silicon, 1 chrome, and 1 moly. This is necessary to obtain a yield strength of 1800 megapascal. And for the process, it's rather simple. We did a quenching to produce a martensite, but martensite is too hard at deformation at the ambient temperature. So then we heated up the 500 degrees centigrade, where the ferrite and the cementite are stable in phase. Actually, this is a tempered martensite, is deformed at this temperature in totally 80% reduction. Then air cooled. So with this process, we can get bar sample with 2 centimeters square, like that. And I should say deformation of a martensite has been called temp-forming by Professor Imao Tamura, who was my teacher in the university. He named this 1963. So what kind of property or microstructure is obtained? And firstly, this is the microstructure before deformation. Then you can see this is a conventional microstructure of a martensite, quenched martensite of medium carbon steels. And when the higher temperature, where the steel is the austenite in phase, grain size is like this. But during the quench, the steel shows the martensitic transformation. Then you can get many kinds of boundaries in it. So as you can see, this is the 10 micrometer. So then purple and the green grains is smaller than 5 micrometer. So originally, martensite structure is a fine-grained steel, even as quenched condition. when the temp formed processing, after 80% reduction at the elevated temperature of 500 degrees C, you can get the elongated grain structure along rolling direction. And the grain size in the transverse grain size is 260 nanometer in this particular observation. And the fine carbide, you can see here, this is a TEM. So the smaller than 50 nanometer. And spherical shape is also plausible for low stress concentration. And the texture shows the strong 101 fiber texture. And this microstructure is similar to that of a cipher that I introduced in the before slide. Then, mechanical property. First, tensile property. This is a room temperature. This is a testing temperature. So you know, BCC steel shows the increase in yield strength as the temperature decreases, like this. Okay? And QT sample is here. And TF is temp formed sample. Okay? Ultrafine elongated grain structure is the higher strength level. But the temperature dependence, I can say it's similar for both type of steels. For ductility, this is a total elongation. I'm sorry. This is a reduction in area. I'm sorry. This is the total elongation. The reduction in area is QT sample, conventional quench and tempered sample decreases like this. It's like a ductile-brittle transition, but that degradation is not so significant for the temp-formed sample. And firstly, we have to check the yield strength. Yield strength here is a 1.84 gigapascal, a little bit higher than the condition of a target of 1.8 gigapascal. Okay? And this is the elongation and the reduction area. And what was the toughness? How was the toughness? Here is the data. So impact energy and the temperature here. This is a case of a conventional case, and this is the upper shelf energy portion. As low as 20 or 30 joule. And the transition temperature range shows here. However, this absorbed energy jumped here, and also inverse tendency of impact energy is obtained like this. And at the ambient temperature, you can see the 250 joule. So marked increase of upper shelf and inverse temperature dependence have been observed. We are so surprised when we look at this data. But firstly, we discussed about this jump. When you look at ductility, the changes are like just here. So then it isn't enough to explain this large jump in impact energy by this ductility. So then we look at flactography. Then finer, deeper dimples in new microstructure has been obtained. This could be one of reasons to this jump. But still, we are examining, we are studying the another or additional reason to explain this jump. Another tendency, the inverse temperature dependence of impact energy is associated with the delamination fracture. Please look at this photo. This is a sample after fracture for a conventional microstructure. This is a case for ultrafine elongated grain structure. So steel behaves like a bamboo when it's broken. And then why this inverse increase is occurred? Maybe associated with this delamination, because delamination more often occurs as the temperature decreases like this. Okay? And then another deformation, fracture mode is seen at minus 100 degrees C. You may ask why delamination improves impact energy. It has been proposed by a research group of Professor Sharby in 1983 with the laminated steel seats like this. You can see the delamination fracture like this. So clearly, the crack branching occurs along the laminated weak interfaces. The delamination relaxes triaxial stress conditions ahead of the advanced crack front and blunts the crack tip when the crack and the crack branching plane intersect. Then further plastic deformation is required to increase the stress of crack beneath. This is the one of reasons why the delamination improves the impact energy. So delamination requires weak planes normal to the striking direction RD. So what are the weak planes in term-formed sample? This is the microstructure for the transverse plane and the longitudinal plane with the orientation mapping with the different color. And when you look at this strong 110 RD deformation texture, then lots of 100 cleavage planes along the RD that is normal to the striking direction. So then the 100 is the weak plane in the BCC steel. So then it would be the plane for delamination. To check it, we observed the flactography. Flactography shows here, well, some zigzag feature and step and terrace, step and terrace. Step and terrace is the parallel to the rolling direction, and that is the longitudinal direction of a sample. And the step is the step plane is parallel to the crack advancing or striking direction. And on step, you can see the dimples like this. However, on the terrace, the precise cleavage fracture mode has been observed. It looks like a cleavage fracture on the 100. So we believe the 100 cleavage fracture causes a delamination fracture in this sample. So then we found this jump from here to here with this medium carbon low alloy steel by processing of temp forming that produces the ultrafine elongated grain structure with the particular texture. So the next topic is the jump in the strength of a bolt. Please look at this. This shows the strength level of high strength bolt for steel construction. Up to 1997, the strength level is around the 1 gigapascal, and no change, no change. Why? This is because of problem of hydrogen embrittlement. We had severe fracture accident at this time and this time. Then to get enough safety, the strength level of a bolt has been kept lower than 1100 megapascal. However, it is because of a strong demand of light, the construction with a lighter material. Here is a jump. Actually, this is pulled by automobile products, automobile bolts, like this. And this jump is associated with the addition of alloying element with the such as the molybdenum, vanadium, and the titanium, and the niobium. Okay? And with the low concentration of impurity of phosphorus and sulfur. So this is the list up of character of this steel, of a new steel, of a both steel. Decrease of impurity, addition of titanium, niobium, vanadium for prior austenite grain refinement, addition of G's for hydrogen trapping sites, and hydrogen embrittlement and MX type carbides. Fracture of hydrogen embrittlement of high strength steel, strength level is here is higher than 1100 megapascal, occurs along the grain boundary because hydrogen segregation reduces the decohesion energy. So MX type carbides act as a hydrogen trapping site and reduce the hydrogen concentration on the grain boundary. So then the target of ultra steel project at the NIMS was to make clear the functions of MX type carbide as a hydrogen trapping site. So for the case of three kinds of a carbide. Firstly, MX carbide is very famous for secondary hardening. This is the matter that you studied in classroom. So because hardness is changing with the tempering temperature, without G's special carbide, this hardness decreases like this with increasing the tempering temperature. However, there is an increase here when the tempering temperature is around 600 degrees C. So this has been observed even in this case. I have to say, I selected the model steel in chemical composition. Okay? This is because our aim is to clarify the mechanism. Okay, so I have to say this is They are not engineering steel in this case, okay? Model steels. And chemical composition has been chosen to obtain a constant atomic fraction of a carbide. And here, when the secondary hardening occurred, you have MX type carbides. Then I checked the hydrogen trapping capability. So this is a little bit complicated. Let me explain. Okay, so this is a hydrogen content. Okay, and this is the condition of a tempering temperature. Let's go back to the figure. So this is the same. Okay, tempering temperature. This is the tempering temperature of a heat treatment condition. And this is that tempering temperature. What we've done is the tempered monazite with hydrogen charged at the constant condition after tempering temperature. And the absorbed hydrogen was measured. And this is the result. That absorbed hydrogen is almost zero when the tempering temperature is lower than 500 degrees C, where the MX carbide does not form. But when the MX carbide exists in the steel, this hydrogen concentration goes up like this. Then again decreased like this. And the hydrogen trapping capacity, this peak level is the highest in niobium carbide, then titanium, and the smallest in case of a vanadium carbide. So the question is arised, why? Even at the constant atomic fraction of a carbide, this kind of a change, a difference in hydrogen trapping capacity has been observed. We did many things to find out this reason. And the result I show you today is a part of that. And because, so I believe this is the essence of the reason. Okay? What we considered is the character of MX type carbide in the atomic scale. Okay? If you are familiar, okay, it's an interface morphology of a carbides. Coherent interface, semi-coherent interface, random interface, something like that. So our case, the interface isn't fully coherent, but semi-coherent. Semi-coherent interface means there are interface dislocations every particular distance, like this. In this case is a titanium carbide. The interface dislocation exists every 4.2 nanometer to fix, to compensate the difference in the lattice misfit of 6.8%. So this is a feature of carbide and interface. And this kind of interface dislocation will be more clear in this photo. If you have a time, you can count the line of atoms. Then extra line would be found like this. So then we discussed the possible hydrogen trapping site for semi-coherent MX carbide. There would be several candidates from the misfit dislocation core to carbon vacancy like this. somewhere normal lattice site here, but the G's possible trapping site, I would like to say misfit dislocation core is the key for this particular case. Why? Please look at your atomic configuration around the misfit dislocation at the interface. You can find the large distorted region along the misfit dislocation core like this. This is the essentially octahedral interstitial site here. So this is the free volume, large free volume, then hydrogen lysis, because the when you have a hydrogen in the interstitial site in the matrix, you have expansion of a lattice. So hydrogen like free volume. So we found it would be a possible trapping site. 2 years later, or I should say last year, it has been found in atom probe research. So the actual trapping site is here. But at that time, so we couldn't use the 3D atom probe. So then what we did is like this. Firstly, we checked the hydrogen concentration per unit interfacial area. Okay, you can see the unit, atoms per square nanometer. That shows the constant value over 1.3 for the different tempering temperature. Please back this data. So hydrogen content or hydrogen capacity decreases like this. However, if you look at here, this hydrogen concentration per unit area isn't changed like this, constant. This is because, okay, the coarsening of a carbide occurs with increasing the tempering temperature. But I was so surprised here. So this is a constant. So then something is here, okay, with this value of 1.3 hydrogen atoms per square nanometer. Okay? So in this case, we measured that we took the many TEM photo and found the size of a carbide and obtained the surface, broad face surface area in unit volume of a sample. And also we found the detrapping activation energy is like this. And what's the meaning of this? Should be related to the sites of hydrogen trapping site. So this is a picture on for interface from the view from top. Okay? And this is the array of misfit dislocation. And what we found is 0.37 nanometer spacing along a misfit dislocation for 1.3 hydrogen atoms per square nanometer. And this spacing is very close to a lattice distance for a long misfit dislocation. So this is a lucky for a good coincidence between two. So then we thought it must be, we believed it must be a hydrogen trapping site. So then we considered further. Trapping capacity would be related to the misfit dislocation density. This is a microstructure feature of three kinds of steel with the different niobium carbide, titanium carbide, and vanadium carbide at the given temperature condition like this. So you can see the different kind of shape of morphology. And if you look at the misfit, and misfit is the larger in the niobium carbide and smallest in the vanadium carbide. Then density of a misfit dislocation is the highest in case of a niobium carbide. That must be a reason for the hydrogen capacity is changing with this order. So hydrogen trapping capacity was like this. And the reason of this tendency would be a dislocation cause a possible hydrogen trapping site, and the higher trapping capacity of niobium carbide is caused by a high density of a misfit. So what we are doing, what we done with this one is to support to this jump that has been done really with the nanoparticles. So I introduced you to two jumps, and it's a time to conclude my talk today. So what I want to say is that steel research is really active even now. So when you look at your steel production per year, is again increasing after steady state of 3 years, I should say 30 years. Okay? And scientific paper on the steel per year is also increasing like this. With this situation, current situation, I would like to say we are now in a new steel era, and the importance of steel and the steel research is increasing now. It is apparent because when the circumstances changed, the demand, new demand of structural materials comes up, like the hydrogen society is giving us the new condition for steel construction. So then we need a research, not only an engineer, but also a science. So this is my controlling remarks today. Okay, so thank you very much for your kind attention to my talk with the nanograins and the nanoparticles. Thank you very much.
So I would like to close the seminar. Professor TSUZAKI, thank you very much again.
Okay, thank you very much for your kind attention. Okay, thank you.